Hi there. So what I'm going to do today is I'm going to talk a little bit about reaction dynamics. So there's a lot of terminology here that you may or may not be familiar with. We're going to talk about what's called activation energy. We're going to talk about the Arrhenius constant, and we're going to talk about collisions and dynamics. It's really an issue of dynamics. Okay, so let me begin. Okay, so this is kinetics. And just so that I have this right, it's 14.4. Okay. All right. So we're going to start by thinking what causes a reaction to take place. We'll call that reaction dynamics. Okay, so for reaction dynamics, the idea essentially is that one particle, now that could be an atom, or it could be a molecule or an ion, and a different molecule. Now it could be the same substance. So each could be like a carbon atom or an oxygen atom or what have you. But what's going to happen is they're going to collide with each other. There's a collision taking place here. Okay, so chemical reactions generally involve some sort of collision. And if you think about it, here's a couple possibilities could happen. So actually, I'm going to give you 3 possibilities. One is they just bounce off of each other, right? So they collide with each other and then they bounce off and they go their separate ways. That could happen. In fact, most of the time when atoms or molecules collide with each other, that's what happens. They just bounce off of each other and go their separate ways. Another thing that could happen is they could kind of stick together, you know, like a piece of lint sticks to glue, you know, to like tape, adhesive tape. So they're not really like they're together permanently, but they're just kind of stuck together. But the third thing that could happen, so we call this like cohesive forces or adhesive. You know, you buy this stuff, it's called adhesive tape, right? So they're kind of stuck together. Here they just, you know, bounce away. The third thing that could happen is actually you get something a little different, which is the electrons from each of these substances start to interact with each other and maybe attract each other to the point where the electrons are not part of one particle or the other, but they're part of both, right? So the electrons kind of spread out in between the two things together and it stays together. And this would be called a reaction. And we would write this, you know, if I gave this, you know, letters, I would say that A reacts with A to form A2, right? A2 meaning the two are stuck together. It's now a covalent bond or ionic bond, most likely a covalent bond, and they're stuck together. This could also be written as 2A goes to A2, right? See, that means the same thing. Now, remember what we said? We said that the rate of a reaction depends on the rate constant times the concentration of the reactants. Now, there's 2 reactants here, right? So, but we don't know what these are, X and Y. Okay, so that's one way to look at it. Or I could say, look, wait a minute, it's the same substance. Why am I writing them out separately? I'm just going to put this. I'm just going to put A to the X, right? Because it's the same material. Okay. Now, this might be, it could be a 2. It could be a 1. We don't know what it is. There's a good chance it's a 2 or a 1. Those are the most common cases. Okay. Now, one question that comes up is, you know, what determines whether they collide and bounce off? What happens? What determines whether they collide and stick to each other? What determines whether they collide and actually a chemical reaction takes place? And there's a couple of answers to that. There's a couple of issues. So we can ask, what determines whether they react? And so one of them is temperature. it's an important one. Temperature is one of the main factors that determines whether things react or not. So for example, you could think of cooking food as a chemical reaction. Cooking food at room temperature takes a lot longer than cooking food at high temperature. So, temperature is a factor in this. Okay. Another thing that is actually what we would call their orientation. So to explain that, let me show this. Suppose that I have a carbon bonded to an oxygen, and there's another reactant, which is just an oxygen atom, and the product is going to be CO2. Okay. Now think about it. Suppose that the orientation of the oxygen atom here is like this. It's moving that way, and this is moving that way. Do you think you're going to get this product over here from this collision right here? Is that going to happen? It's not going to happen, right? Because this oxygen's on the wrong side. It needs to be all the way over here. So if the orientation was like that, and now the collision's going to, oops, sorry, I changed both of them. So now the oxygen atom's over here. So this one's moving that way, and that's moving. If the collision was like that, then you got a chance of it happening, right? The orientation is proper. And so maybe you could actually get your product. Okay, so orientation is another issue that's important. And sometimes what happens is in chemical reactions, the molecule that's reacting might be really, 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 really big. So it might look like that. Those are all like atoms bonded together. It might have hundreds of atoms. And so maybe the other reactants, like this little thing right here, is just like maybe 10 atoms. So this guy right here, in order to react, let's say that it has to be right here in order for the reaction to take place. The chances of it being in the right orientation are very low, right? Look at all these different directions it could be, or positions it could be, without it actually being in the right spot. It's a lot of them, right? It's got to be all the way down in there, right? So every time these collide, it's just going to bounce off, bounce off, bounce off, bounce off. Not very many products out of that, okay? Now, what I want to do is focus on temperature, because this section is what I call reaction dynamics, but Alex says it's the temperature that we're concerned with. So let me show you what I want to talk about this right here. Imagine that in order for the reaction to occur, so I'm going to have two atoms that are bonded together here, and let's say a third atom is going to come in here, and it's going to react by forming a bond here. But suppose in order for this to occur, one of the requirements was that this bond break. Let's just say that has to happen. In order to get what we want to get Ca, let's say, plus B, right? In order for this to happen, this bond has to break. Well, how is that bond going to break? One way it could break would be that the C hits the A so hard that it essentially transfers energy into this bond and breaks the B off, and it comes off as a separate atom. Okay, this is a cartoon, but essentially it's the idea that we're talking about. In other words, the impact is important, how powerful that connection, that collision is. And we would say that it has a certain amount of energy of collision. And so that's why temperature, one of the reasons that temperature is such an important factor in terms of how fast reactions go. The higher the temperature of a reaction, the faster the molecules are moving. So at low temperature, the molecules in your container, in your reaction container, are moving very, very slow. But at high temperature, these molecules are moving very fast. See how I'm drawing the arrows longer? Well, the faster they go, the more energetic they're going to hit each other, and the more chances there are to break chemical bonds. It generally, in order for a reaction to take place, it usually requires some bond to be broken, or more than one bond to be broken, and then new bonds are formed. Okay. Now, I want to show you a problem here that kind of connects this in. It's an important type of graph, and it's one that you want to be able to analyze. You may have seen this in other courses. Sometimes people show it in biology courses. Okay. Here we go. So consider a hypothetical chemical reaction where A plus B is reacting to form C plus D. In the equation A, B, C, D are some chemical formulas, right? H2, O2, H2O, whatever. Here's an energy diagram. So this is called an energy diagram. The energy diagram typically on the y-axis is energy. So the further up you go, the more energy that the reactants and products have. The further down, the less energy. And then reaction coordinates, a little tricky. You can think of it almost like time. Something is happening over time. Okay, so we would start here, start a clock, and then as time goes on, it's going to increase in time. So now let's take a look at this. This has the reactants here, right? A and B are reactants. They have a certain amount of energy, 300 kilojoules per mole together. The products have less energy, right? So where'd that energy go? If you have more energy and now you have less, the energy had to go somewhere. And typically in a chemical reaction, it goes into the environment. It heats things up. It's called heat transfer, right? So energy goes somewhere else. That's an exothermic process, right? If I start off with 300 kilojoules of energy, and now I only have 250 kilojoules of energy. Why 250? Look at the scale. 200, 250, 300. I lost 50 kilojoules of energy. That's exothermic. It goes out somewhere. Okay, so you never destroy energy, you just transfer it. So if the energy goes down, that's exothermic. So the difference in energy between your starting point and your final, that's going to tell you how much enthalpy change you have, whether heat is coming in or out. In the case where the products are lower in energy, that's exothermic. In the case where the reactants are lower in energy, then that would be endothermic. So if you go uphill, that's endothermic. Another issue here is what we would call the activation energy here. The activation energy is the difference in energy between the reactants, not the products, but the reactants and the peak here of this hill. It's often referred to as an energy hill. That difference in energy, which is 100, right? 300 to 400, that is called the activation energy. The activation energy is typically written as a capital E with a lowercase or a subscript A, activation energy, energy activation. Sometimes it's EACT, sometimes it's EACTIV, but it's typically E with an A down below, okay? So this is essentially the energy required to break chemical bond. Now, we don't know what bonds are being broken here because we don't know what these substances are. A could be H2O, so you're breaking an oxygen-hydrogen bond. B could be NO, you're breaking a nitrogen-oxygen bond. We don't know. But bonds are going to be broken here, and then bonds are going to be formed here. And notice what happens. The formation of bonds lowers the energy. So it's usually downhill when you're forming the bonds. So you put energy in to break the bonds, you get the energy back out to form the bonds. And look what happens. Only 100 kilojoules of energy to break the bonds, but the formation gives you 150 kilojoules back out. So there's more energy produced by forming the bonds than there is in breaking the bonds. So we call that exothermic. If the bonds of the products are stronger, they're going to be lower energy. So here they're lower energy, so these are stronger bonds. These are higher in energy, so these are weaker bonds. Okay, so let's look at the questions. What is the heat of reaction? That's delta H. That's the difference in energy between the reactants and products. It's negative 50 kilojoules per mole. Why negative? Because you do products minus reactants, final minus initial. Products are over here, 250. Reactants, 300, 250 minus 300 is minus 50. Exothermic. If the products are lower in energy, that's an exothermic process. If the products are higher in energy, so let's say it went like this, and then came out over here, that would be endothermic because now you'd have 350 for your products. Can you determine the activation energy? Absolutely, yes, you can. It's the difference in energy between the reactants and the peak. So that would be 100. You start here, 300, go up to 400, that's 100 change. It's gonna be positive. Now, by the way, if I gave you the reverse reaction, we'll talk about reverse reactions in another section in the next chapter. We could go backwards. Suppose these were the reactants and these were the products. So now your delta H would be plus 50, right? Because this would be final, this would be initial. So going backwards, you change the sign of delta H. And your activation energy would be higher. You'd have to go from here all the way up to there. That would be 150 would be. So this only has 100, but the reverse reaction would have 150. But they're just asking activation energy. So that would be from A to B to the peak. Can you determine the activation energy of the reverse? Okay, so I was thinking a little bit ahead. That's actually what they're asking here. So if you do the reverse reaction, the activation energy would be from here up to there, which is 150. Okay, so there's that problem. Back over here. That's kind of a fun problem. Hope you enjoy that one. Okay, now we're going to look at a problem where we're going to get into some calculations. Okay. Understanding the qualitative predictions of the Arrhenius equation. Now, this is the Arrhenius equation, okay? So the Arrhenius equation is a mathematical relationship that tells us the relationship between temperature and the rate constant. Remember, the rate constant is essentially a measure of how fast the reaction is going. And there's different forms of the Arrhenius equation. Okay, so I've got one there. I just want to make sure I show you a couple of them. Okay, here we go. That's one of them. Okay, so a certain reaction is known to have an activation of 72.0 kilojoules per mole. Furthermore, the rate of reaction is measured at 366 Kelvin. Temperature, that's right, Kelvin. Found to be 5.3 times 10 to the minus 3 molar per second. That's the rate. Use this information to answer the questions in the table below. Suppose the concentration of all reactants is kept the same, but the temperature is raised 10% from 366 to 403. Okay, they actually told you the two temperatures. Thank goodness. Okay. Suppose the concentration of reactants is kept the same, but the catalyst is added, which has the effect of lowering the activation energy by 10% from 72 to 64.8. How will the reaction rate change? Okay. Now here's for this problem. Okay, let me stop share here. For this problem, okay, let me spell this out for you. Arrhenius. That's the person that came up with it. Svante Arrhenius. Actually, I'm sorry. It's either Gustav or Svante. I met the grandson, and I've gotten the two names mixed up. The one I met, I think, was Gustav. The actual Arrhenius that did this equation was Svante, I think. Okay, so here's the equation. It actually doesn't have rate in it. It just has the rate constant. Okay, I can write it that way, or you can write it this way. Same thing. I'm just using a slightly different modified way of writing it. And actually, I have a tendency to put the negative right there. But I mean, you know, it really should be just in the front of that fraction of that ratio. Okay, that's a little better to write. Okay, so this is called the Arrhenius constant. The Arrhenius constant is essentially a measure of how frequently these things are colliding with each other. The molecules are bouncing around colliding. It's a measure of how frequently they collide. More specifically, it's how many times they collide with each other times some factor of orientations. But roughly speaking, it's how often they're colliding with each other. So it usually has a unit of like 1 over time. Like if something collides 10 times a second on average, units would be 1 over seconds. Okay. This is the activation energy right here. Okay, remember what the activation energy is from that graph? It's the difference in energy between the reactants and the maximum, the peak. That's your E sub A. Okay, it's usually in kilojoules per mole. This is temperature. And then this is the gas constant. Okay, And that's the equation that we can use for this particular problem. Oh, it's a little tricky though, because if I use this form, then you won't obviously see what's going on. So I'm going to modify it a little bit. I'm going to take the natural log of both sides. Okay, so we can write it that way too, which is most usually modified so that we put the E sub A over R first times 1 over T, and then plus the ln of A. Now, here's essentially what happens. If the temperature goes up, that's going to make this ratio smaller, right? If you make that denominator a little larger, it's going to make the ratio smaller, okay? So if this ratio here is smaller, then this whole term here is going to get smaller, right? It's going to make that whole thing smaller. But that affects the ln of k in a way that's not intuitive. What happens is, if I make this thing smaller, that's going to affect k in such a way that it actually gets bigger. Kind of funny, right? And it has to do with this negative here, and it has to do with the nature of natural logs and how they relate to negatives. So in a sense, what I'm going to do is I'm going to say this. If t goes up, k is going to go down. That's mathematically the way it works out. If t goes down, k is going to go up. Okay. Oops, I'm sorry. Do I have that the reversed? I have it completely reversed. I'm sorry. Sometimes I do that. If t goes up, k goes up. If t goes down, k goes down. Okay, that's the relationship. Okay, T being temperature, K being rate constant. Now, rate is equal to K times the concentration of your reactant, right? To some power X. So if K goes up, rate goes up as well. So in this particular question, they're not telling you the rate constant, they're telling you the rate. But rate and rate constant are proportional. So if they say the rate went up, really what they mean is the rate constant went up. Okay, they're telling you K is there because the rate is not in this equation. There's no rate in here. It's just rate constant K. Okay, and this value right there. Okay, so this is the relationship you want to remember. If T goes up, K went up. If T goes down, K goes down. Okay, that's essentially the relationship. So let me come back to this problem and we'll take a look at it. Suppose the concentrations of the reactants are kept the same, so we're not changing anything about the reaction except the temperature. It goes up. How will the rate of the reaction change? Like I said, if T goes up, K goes up. If K goes up, that means it's going to be faster. So the rate will increase. Okay. Suppose the concentrations of the reactants is kept the same, but the catalyst is added. Now they tell you in here, that has the effect of lowering the activation energy. So how will the reaction rate be changed? Okay, now that is an interesting point, and I want to, here, I'll show you this. Okay, what a catalyst does, it stabilizes what's called the transition state. Okay, so let me show you what a transition state is. Suppose I have A going to B, or A bonded to B reacting with C, and we have to break that bond between A and B, and then we form a new bond between B and C. See what's happening? We're going to break this bond. And then we're going to form this bond. Okay, so if we come back to our energy level diagram, E for energy. Here's our reactants. Come up, activation energy all the way up there and then come back down. Okay, we're going to do it that way. Remember what we said, the activation energy is right here? E sub A. Okay. What's happening is A, B, that bond is breaking, and then you're forming A plus BC, new bond being formed here. While this process is occurring, okay, it's a dynamic process. A and B are breaking their relationship. Breaking the bond requires energy. So you start going uphill to break that bond. But then see how it doesn't go just straight up. Over time, it's kind of gradually lumping over, turning over, and then it starts going back down again. What's happening is during this process, you're starting to form this bond. As that bond forms, the whole energy starts to go down. So you have two competing processes. One that's causing the energy to go up, which is the breaking of this bond. And then one that's forming this bond right here is starting to pull it down. Okay? So what a catalyst does is it makes this whole process lower in energy. The whole process of breaking and forming the bond. So let me change the color. If you add a catalyst, it lowers the activation energy. It doesn't change anything else, quite frankly. It's still going to end up at the same energy. It doesn't change the products. It doesn't change the reactants, but it changes the dynamics of that process while it's occurring, lowering its activation energy. Okay. Now, what that does then is it makes it so there doesn't take as much energy for this reaction to occur. So if two things are colliding, but they're moving slower, if the activation energy is lower, they could still form products. Whereas if the activation energy was higher, they don't have enough energy to break the bond. Okay, so in a sense, what it's doing is it's lowering the energy to break the bond, making it easier for the reaction to occur. So the tendency then is if you lower the activation energy in any way, catalyst is the most common way to do it, the reaction will go faster. So if you lower the activation energy, K, the rate constant will go up. So instead of raising the temperature to make it go faster, you can use the same low temperature, which saves you energy, heating costs, right? In the winter, if you're in your house and it only has to be 50 degrees inside, that's not going to cost as much energy as if it has to be 75 in your house. So less energy required. Sometimes high temperatures will break things and you don't want that to happen. So lower temperature can sometimes be better. All right. So lower activation energy through catalysts will increase the rate constant. And remember, rate is proportional to the rate constant. Higher rate constant, faster reaction. So having a catalyst will have a tendency to make the reaction go faster. Okay. So if we come back to that question then, part three or part two? Part two. If we lower the activation energy, okay, so it went from 72 kilojoules to 64.8, the reaction should go faster. The rate of the reaction should be higher, it should be faster, okay? So two ways to make a reaction go faster. Raise the temperature, that'll make it go faster. Add a catalyst. Now, sometimes there aren't catalysts for reactions. We may not have a catalyst, or maybe the catalyst is so super. In fact, here's an example of a catalyst, a catalytic converter in a car. Usually uses these very exotic metals like platinum, rhodium, I forget the other ones, very expensive. So people steal catalytic converters. They make the exhaust of your car get converted into less toxic materials that don't damage the environment, supposedly. So people will steal catalytic converters because those metals are very precious. Okay. All right, there we go. So there's that question. Let me see if we've got any others in here. Okay, let me show you this one. This is just sort of a real calculation problem. The other ones were conceptual. Using the Arrhenius equation to check K, the rate constant, at one temperature from K at another temperature. It doesn't say another temperature, but it means another temperature. So K is a constant. Is it a constant? K changes if the temperature changes. So we remember how we said K is a constant? Only if the temperature is constant. If you change the temperature, K will change. The rate constant of a certain reaction is known to obey the Arrhenius equation and to have an activation energy of 10 kilojoules per mole. If the rate constant of the reaction is 1.1 times 10 to the 7 per molar per second, by the way, that's second order, at 262.0 degrees C, what will the rate constant be at 207.0 degrees C? Okay, this is what we would call a plug and chug problem. I'm going to show you the equation that you use for this one. It's ln of K1 over K. There's different versions depending on where you look. Sometimes they put K2 over K1 and then they swap out the T's. I just looked online and it's K1 over K2 for this version. Minus E sub A over R. Well, I'm going to put the negative in front. I'm sorry. Times 1 over T1 minus 1 over T2. Okay. There you go. All right. So this is an alternate form of the Arrhenius. It's done by doing this. ln K1 equals minus E sub A over R times 1 over T1 plus ln of A. And then taking another version at a different temperature. Because what happens is as you change the temperature, you change K. Doesn't change A, doesn't change R. R is the gas constant, but it changes K. So what you do is you combine these two. And I'm not going to go through the arithmetic of combining them. It's fun, but I'm not going to take the time to do that for you. So it's right here. This is the equation you want to use, okay? So in this particular problem, usually what they do is they say, hey, here's a temperature, and they give you the value of K, K1. Here's a new temperature. We want you to find the value of K2, okay? Now, what I can do is I'm just going to modify it a little bit. I'm going to put K2 over K1, but if you're going to do that, you have to change something. You have to put T2 minus T1. So if you changed where the K's are here, you change where the you change which one's plus and which one's minus in the T's, okay? I like this form more because generally we're given a value of K, so we call that K1. Find a new K, so that's K2. And it's just a little bit easier to have the K2 here on the top, okay? This can be written as ln of K2 minus ln of K1, okay? It's a logarithm issue. Ln of B over A equals ln of B minus ln of A. So I'm just doing that there. Okay. All right, let's go through the problem. I'm going to come over here. Okay, so I'm going to start writing down the information here. Here's what we have. E sub A equals 10.0 kilojoules per mole. Okay, there's your E sub A. They tell us K is equal to 1.1 times 10 to the 7 molarity to the -1 seconds to the -1 at 262 degrees C. Then they say we want to know the new K. So I'm going to call this 1 and I'm going to say the new one is 2. What is it? That's what they ask us to do at 207.0 degrees C. Okay, that's the question. They want you to round it to 2 significant digits. Okay, that's the question. You can go back in the video and see what it looked like. I'm going to erase a bunch of these equations here because I want to be able to show you the problem where I just wrote all those numbers down, okay? So let me just erase all of this. Couple things. Temperature needs to be in Kelvin. Okay, so first thing I'm going to do is I'm going to say T1 is 262 0.0 plus 273.15. We got to convert that to Kelvin, okay? So let me do that on the calculator here. 262 plus 273.15. It's got to be in Kelvin. 535.15 Kelvin. T2 is 207. Got to convert it to Kelvin. It doesn't work in Celsius. Celsius is a terrible scale. It is not a valid scale if you're doing energy calculations. So 207 plus 273.15, 480. Wait a minute, that doesn't seem right. Oh yeah, it is. It's lowered. They lowered the temperature. I thought they raised it. Okay, it went from 262 down to 207. Okay, get colder. Okay. Now, we know K1, that's going to be our original value of K, 1.1 times 10 to the 7, molarity minus 1, seconds minus 1. Okay, what's R? R is the gas constant. You're going to use the 8.314 joules per K mole. Don't use the 0.08206 that you may have learned in Chem 11. Use this value right here, energy units. Now, energy, activation energy is in kilojoules. We want to have it in joules. So this is 10,000. 10 times 10 to the 3 joules per mole. What did I do? I did a conversion from kilojoules to joules. Okay. 10 times 10 to the 3, 10,000 joules per mole. Kilos 1,000. That's 10 to the 3. Okay, so I did the conversion there. Now you can come back to the formula. And remember, I changed that formula up a little bit. I put it as ln K2 minus ln K1 equals minus E sub A over R times 1 over T2 minus 1 over T1. Is that right? Do I have that right? I hope so. Wait a minute. Let me see. It was 1, 2, 1, 2, 2, 1, 2, 1. Okay, that should be good. Okay. So now what we're asked to determine is K2. So I'm going to put a box around that. If we want to find that, we want everything on the other side. So I'm going to add this to both sides. Right? Like if I have 6 minus 2 equals 9, and I add 2 to both sides, now I have 6 equals 9 plus 2. Okay. The arithmetic didn't work out there. Plus X, we'll put plus X, okay? Okay, so this is gonna be gone, and that's gonna give us ln K2. So now we have minus E sub AR over R. So minus 10, where did I put that? 10 kilojoules per mole. Oh, I put it up here, sorry. 10 times 10 to the 3, okay? That's 10,000. So you can go ahead and put 10,000. Joules per mole, right? Kilojoules, it was 10 kilojoules, now it's 10,000 joules. Don't forget the negative. And divide that by R, 8.314 joules per K mole. Okay, look what happens. Joules cancel, moles cancel. You just got 1 over Kelvin. This is going to give us the units of Kelvin, just so you know. Okay, so equals. I'm having a problem writing it on the same line. Now, 1 over T2. So 1 over 480.15 Kelvin. Okay. Oops, not in print. No, don't close the parentheses yet. Minus 1 over 535.15. Okay. So now just go through the arithmetic. So I'm going to do the 10,000 over 8.314. I'll do that separately. 10,000 over 8.314. So it's 1203. So this would be minus 1203. Remember, the units here cancel, so you just had 1 over Kelvin, so that's just Kelvin. Then let's do this arithmetic. 1 divided by 480.15 equals minus 1 over 535.15 equals. Okay. Now, that gave me a really small number, which I guess could be right, but I just want to check. I'm going to put it into scientific mode here. It's usually better to do these in scientific mode. So 480.15 reciprocal, 1 over x, minus 535.15 reciprocal, and then equals, yeah, I got the same answer. 2.14 times 10 to the minus 4. And this is going to be 1 over Kelvin because there's no units up here, but there's a Kelvin there. Now you multiply those two numbers together. So times 1203 negative. Remember, it's negative 1203. And you get that and then plus ln K1. I'm so sorry. Plus ln of K1, and K1 was 1.1 times 10 to the 7. I'm not going to put the units in there. Okay. So here's what we get now. Now I can erase this over here. We don't need to have this here because we put the new temperature up there at the top. Okay. So again, I know it's a little messy here. ln K2 is going to be minus 1203 Kelvin times 2.14 times 10 to the 4 minus 4 times 1 over Kelvin plus ln of 1.1 times 10 to the 7. Okay. All right. Now, let's do the ln of 1.1 times 10 to the 7. Very easy. You go 1.1 EE7. Okay, that's 11 million. Okay, let me do it again. 1.1 EE7. Now, I'm going to take the natural log, ln, and I get 16.21. Okay, so this is going to be ln of K2 equals, now, I'm going to write here. We're going to get a number here, and I'm going to say plus 16.213. Okay, so that's what I got for that right there. So now 1203 negative times 2.14 times 10 to the minus 4. So I get minus 0.2574. Okay, good. Now you add those together. One's negative, one's positive. So you get ln K2 equals 15.956. Now, to get K2, we have one more step. Okay, so I'm going to bring it all the way over here. Last step. We've done this whole thing here. Now we want to get K2. Here's what you do. If you have y, ln of y equals x, what you do is called the inverse function. You take e to the ln of y equals e to the x. And then it turns out e to the ln of y is just y. So it follows that y is just e to the x. So all we have to do is do e to both sides. So e to the ln, I'm not going to do it down here. I'm going to move it up here because we've got some more room. E to the ln of K2 is going to equal e to the 15.956. But e to the ln, they eliminate each other. So you just get K2 is e to the 15.956. Now you can't enter it in like this. That is a number. Mathematically, that's a number. But you got to express it in decimal notation. So, or scientific notation. So what you do is you take 15.956 and you do e to the x. And K2, we only need 2 significant digits. So I'm going to put it as scientific notation, 8.5 times 10. Let's see, 1, 2, 3, 4, 5, 6. Okay. Yep, there we go. It came out right. And there's your K2. Okay, a lot of steps in that, right? So let me let me show you real quickly what you're doing. Okay, there's your answer, 8.5 times 10 to the 6th. What you're doing is you're taking this equation here. Okay. This was given right here. That's a given value, but you have to convert it from kilojoules to joules. This is a constant. You have to have that value with you, right? That's a known constant. This needs to be in Kelvin. This needs to be in Kelvin. You're doing a lot of conversions in here, right? Well, not a lot, but you're doing a couple. You're doing Celsius to Kelvin and you're doing kilojoules to joules, right? So that's not a lot. Then you plug all those numbers in and just do the arithmetic. But be careful, because when you're doing that, there's so many ways you can make little mistakes with your calculator. So I recommend have like step 1, step 2, step 3, step 4, step 5. Really write these numbers down so that you don't make, you have to have very good organization skills to not make mistakes here, or to, when you make a mistake, to find out where you made your mistake. So it might take 14 steps, but you got to do that, right? I recommend it anyways. And then you get K1 is given, so you just have to know your calculator how to do that, okay? And then you're just going to solve for this. You're going to put all those numbers in and solve for this. And then you're going to, the last step is, once you get ln of K2 equals, I don't know, I'm going to make up a number, 7.35. You just do e to that. And your calculator can do this very easily. Just do the e function, okay? And then that's going to be K2. That gives you the value there, okay? So it's kind of a fun problem. It takes a little bit of effort. You might have to practice it a couple times if you're not real good with your calculator. That's really what it comes down to. But there you go. Okay, there's one more. I'm going to just show you a little bit of detail about that. I mean, not much detail about this one, but I'm going to show it to you a little bit. The strategy anyways. And that's this one right here. See how they give you 2 temperatures and they give you 2 values of K? Same thing, Arrhenius equation. But here they want you to find activation energy if you've got those 2 sets of data. 2 temperatures, 2 values of K, find the activation energy, okay? It's really just using that equation the way we just did it, but you're just modifying it a bit. So again, we had this, right? ln of K2 over K1 equals minus E sub A over R times 1 over T2 minus 1 over T1. Okay. In this case, they give you both temperatures and they give you both Ks. So just put your numbers in here, calculate a value, get a number out of that. That whole thing will give you a number, right? So in this particular problem, they told you, that at 141 degrees C, the value of K was 1.8 times 10 to the 11. And at 256 degrees C, the value of K was 3.2 times 10 to the 11, right? So you have those 2 values, so you can get a number out of that. How do you do that? You just take the ratio. So you go 1.8 times 10 to the 11 divided by 3.2 times 10 to the 11. And you just take the natural log of it, take the natural log of that ratio. So you're going to get minus 0.575. Okay. Now that's equal to what we have over here, right? So now, minus, this equals minus E sub A over R. And then let's just put some numbers in here. Your T2. Now remember, this has to be in Kelvin. So your T2, you got to add 273. So it's 256.0 plus 273.15 minus 1 over 141.0 plus 273.15. Okay, and then that whole thing. Now you be careful about that, right? Okay, so 256 plus 273.15 equals 1 over x. So you get equals minus E sub A over R times 1.889, I'm sorry, 890. Times 10 to the minus 3 minus 141 plus 273.15. Take the reciprocal. 2.415 times 10 to the minus 3. Okay. So now let's take that difference. 1.89, are they all 10? They're both times 10 to the minus 3. So 1.89 minus 2.415, and you get minus E sub A over R times 5.25, it's minus, sorry, times 10 to the minus 4. Okay. Now notice, if you have a minus here and you have a minus there, you can just cancel them. So this is the same as EA over R times plus 5.25 times 10 to the minus 4, right? Minus a minus, you have two minuses in there, okay? So now let's do this. We already did this way back here, don't forget that. Okay, so we have minus 0.575 equals E sub A over R times 5.25 times 10 to the minus 4, right? So now I just need to find E sub A. So I'm going to multiply both sides by R. Put it in parentheses just so that we don't lose track of where we are. What was R? 8.314 joules per k mole times 5.25 times 10 to the minus 4, and that equals E sub A. See how I did that algebra? Review it, watch it a couple times, see how I did if you're having problems with that, okay? So now 0.575 negative, make sure you have that as a negative. Oops, there's something wrong there. We should not, oh, well, first of all, it's divided by, I'm so sorry. We're trying to find this, so we're gonna multiply and then divide by this one here. Okay. Okay, so now there is still a little bit of a problem here. Somehow I ended up with a negative, and that should not be a negative. So somehow I made a mistake here, okay? So let me see if I can track back. We've got 3.2, oh, I see. K2 over K1. So I had these reversed. So it's, I'm so sorry, it's 3.2 times 10 to the 11 over 1.8 times 10 to the 11. Now, the nice thing about that is that just makes it a positive. If you take the reciprocal inside the ln, it just makes it a positive. So this is positive. So let me just make sure I go through here. Everywhere that I did that 0.575 needs to be a positive. There we go. Okay, now it's good. That's a 4, by the way. Okay. So now 0.575 times 8.314 times 10. It's just 8.314. 0.575 times 8.314 divided by 5.25 times 10 to the minus 4. And okay, now that's a minus 4. Okay, so you get 9106 joules per mole. Okay. Now that's way too many sig figs. They said just round it to 2. So that's approximately equal to 9,200 joules per mole. Now, I will say this, that typically speaking, when you're dealing with activation energy, they are going to want it in kilojoules per mole. So you have to convert it to kilojoules. So 9,200 joules per mole, 1 kilojoule is 1,000 joules. So you're going to get 9.2 kilojoules per mole. Okay. All right. So that's, which is actually not a very big one. It's about 9 kilojoules. Let's see, that makes sense. You went up. Yeah. Well, actually, I don't think that would be, I would think we would be off there. Let me just check. Yeah. Okay, they got 9.1. I'm so sorry. They got 9.1. I got 9.2. Which is not that far off, but it's probably enough that it's going to cause you some problem with the way they're doing stuff. So let me just make sure. 3.2 divided by 1.8 equals, take the natural log, 0.575. 4. I guess I'll leave an extra digit there. Make that a 4. Man, that's so close. That would be a frustrating thing if you got it wrong just because you put 9.2 instead of 9.1. But I suspect what's happening is they're using a slightly different version of R. Instead of 8.314, they're probably using a lot of significant digits. Here we go. 8.31446. Okay, so it's a little bit bigger there. When you do the calculation, you're multiplying by 4, so that would make it a little bit bigger. So, oh, wait a minute, I'm sorry. I had 9106. So why did I round that to 9200? That's my problem. Making a little silly little errors here, right? 9.1, so it's 9.1 kilo. So we did have it right. Okay, so it wasn't really a significant digit. I just did a poor job of converting this to 2 significant digits. Okay, so 91, so this is 9100 joules. So we got it right, perfectly right. Okay, excellent, good. So that is the end of section 4, which is the dependent of the reaction rate on temperature. See, I went through every type of problem that's in that section, so hopefully that will help you. Okay. Take care.